An action potential is a communication or an impulse that is sent down the axon. Sent down axons. So if we look at this graph here, so we have our potential or our millivolts on one side, time on the other. We know that a resting membrane is at -70. Got +30 up here. And then right here we have about -55, which is going to be important in making these action potentials fire, okay? So an action potential, we have a resting neuron here, and an action potential is started or triggered by a graded potential. We already said that. The graded potential, as it's traveling across the cell body of that neuron, is increasing the potential of the membrane a little bit. It's increasing and increasing it. And if it increases it enough, then it will get to what's called threshold. So this is the threshold number. And once it gets to threshold, then it goes. And it goes all the way. So once it gets to threshold, then voltage-gated channels open for sodium, and we get depolarization. So sodium comes in, and that is called depolarization. Okay, and then potassium gates then are opened, and just don't forget there's more sodium outside, so sodium's coming in. That's why it's depolarizing, because you have all those positive ions coming into the cell. And when the potassium channels open, potassium leaves the cell because there's more potassium in it. So the potassium is leaving the cell, and that will cause repolarization. Because as those positive ions leave, it's making the inside more negative again. Once we get to resting, which is -70, the gated channels that are open for potassium are kind of slow to close. So the potassium causes sort of an overshoot, which is called a hyperpolarization here. So the membrane gets a little bit too negative. It gets below -70. And then we have the sodium-potassium pump. The sodium pump to bring it back to resting at -70 millivolts. This whole process comes from the permeability of sodium and potassium. And remember that when sodium gates are open, the gradient is going to be fast. It's going to come in quickly, and that's going to cause the depolarization. When the potassium channels are open, potassium is going to leave, but it's going to leave a little bit slower because there's already a bunch of leaky channels for potassium in the membrane. So that is an action potential. Okay, it goes from -70 to +30, so about 100 millivolts. And it always looks like this. Always looks the same. They all look alike, okay? These are long distance signals. And they are propagated all the way down the axon. So it goes from the axon hillock, where it's stimulated, all the way down to the terminals. So if we show a little, here's my cell body, here's my axon hillock, and then here's my axon, and we'll go out here to these little terminals here. So if this is the neuron, then on the cell body or on its dendrite or whatever, there is going to be a graded potential that is created here. Okay, so there's a neuron that is associated there. So there's some axon terminal with another neuron attached to it, and it's sending out a signal, sending out neurotransmitter. The neurotransmitter is binding to the plasma membrane here, those chemical gates, and we're getting a graded potential. That graded potential moves down till it gets to the axon hillock. And at the axon hillock, there will be gates, voltage gates, or voltage-gated channels for sodium. And when that potential, if it is strong enough, and it gets the membrane to -55, then these voltage gates will open, and sodium will come in, and it will be propagated all the way down the axon. That action potential, once it goes all the way down to all of its terminals. It does not stop. It does not dissipate. Okay? It either, if it gets to threshold, it's going to go. So if the membrane gets to threshold, the action potential will be triggered. And it will go all the way to the terminals. That is called the all or none principle. So it either doesn't go at all or it goes all the way. Okay, there's no middle ground there. Okay. So again, action potentials only occur on the axons. Okay. They all look alike. So we know that a graded potential, the strength of it, is based on the amplitude of its tracing. But in an action potential, the tracing is always the same. So how do we know the strength of the stimulus? The strength of the stimulus comes from the number of action potentials firing. Okay, So the more action potentials that come down here, the more neurotransmitter is going to come out of these terminals. Okay, so that will dictate the strength of stimulus for the action potential. So now we're going to compare and contrast graded potentials and action potentials.